Okay, so we will be get back to the room, to classroom for the lab very soon. Okay, that's what I'm working on now. The way will be we get a two shift, one from 3 to 5, and another one from 5 to 7. And Tuesday, Wednesday, Thursday. And also we get 2 rooms. We get 6 lab system in one room. So for each shift we get 12 people. One day we get 24 students. Okay, to do the lab. So at this time, you get only one day meeting with me on the Zoom. And the rest will be doing your lab. Okay, so any question about that?
So are we going to start from the next week?
No, not yet. I'm working on. Okay.
Okay.
But I believe we will be very soon.
That's a good news. Good news.
Yeah, that will be a very good news. So that means you get only one day lecture on Monday. And the other one will be doing the lab. And the texture will be one day, will be on Tuesday. Okay, so
Mr. Fran.
Yeah.
Not everybody's going to be in class at the same time, correct? In the lab?
In the lab, no, only 12 people at a time.
Priority students only, correct?
Can you say again? What I'm saying is only 12 students in the class.
So that means my turn will be once in a week, one time in a week. Am I right? One day in a week.
Depends.
Okay.
I try to see how many students active so I can assign for the lab time. So basically you can get 3 days, you can get 12 people, 24. That means you get 12 people from 3 to 5 and another 12 from 5 to 7. So 24 students per day. 3 days you get 72 students. So you can get, I think you can get more time in the lab.
How many days a week for class then? If
3
only
days.
3 days, only 3 days a week. All right.
3 days and 1 day for lecture.
So the 1 day lecture online?
Online?
On Monday.
And then what about the other days where no students are accessing the lab, since there's only 24 people each day?
Yeah. That means you have to do your homework. The thing is, you understand, we don't have enough instructor to do it. Each instructor, they pay only around 14 hours a week. So that's why.
How many days officially for school if only 24 people can go to class only one day a week?
1 day, but that not mean a week. You can go 2 days, depending on the number of students.
But only 2 hours at a time.
Yeah, only 2 hours.
I'm sure you'll figure it out. You'll let us know, Mr. Pham. Thank you.
And then on Tuesday, you said it's the Tech 2, right, Mr.
Right,
Pham?
lecture.
Okay. So since I'm taking Tech 1 and Tech 2 together, so that means you'll be assigning me to either Wednesday or Thursday for lab then.
Right, normally every week before we started, they get a list for you guys from what time to what time.
Okay. All right. Thank you very much.
The thing is, when you get into the lab, a lot of things they need to check, like you go to work. They have to take the temperature before you can come to the room. When you get into the room, we get everything for your assignment in what lab you will be working on. And they get enough on of the thing to clean up whatever. After you done for the lab, have to clean it up again before you leave it for next one. And also, the way will be if you get a problem. So into room, we can get the projector and also we can get the Zoom. So you can go into the Zoom and chat to the instructor, ask you get a problem on what. Then they will be using the Zoom to help you out. No contact at all. The worst case is we cannot fix it for some reason. Then you have to go into the safe lay and sit there, and the instructor will be look over to see is it a system problem, is it a circuitry problem, and he have to fix that. Then you can return to working on. That means we don't want any contact. Okay,
Got it.
that's safe for you, safe for the instructor, safe for everyone. And if you're not assigned, cannot get into the room. That's a safety requirement.
Hey, Mr. Pham, I know you want to get started with the class, and I don't want to continue on with all these questions for something that probably is not going to be resolved until probably at least January. But my question is you said something about they have to do the temperature thing, because I know when I went to see my dentist, they put a temperature thing up near your head and they got to take a temperature. What's going to happen when people are failing the temperatures or other issues are coming up? How are you going to be able to run that?
If a failing temperature, go home.
Oh, yeah. So
Totally.
it's better you measure your temperature at your home before going to the lab.
That normally company, they do it that way. City asked for doing that way also.
So,
That's safety for everyone.
I guess what I'm saying is I see some, I'm not going to get into it, but I see some issues coming up where you haven't talked about, but I'll just let it wait till down the road and then see what happens.
Okay, the thing is on textual will be we try to set up. Okay, so you will be take out the tool and do it home.
So you're saying Tech 2 is going to be set up where you just basically give out like parts or whatever, and then they go home and do their stuff. But mostly the at the building is mostly going to be for Tech 1.
Yeah, only for Tech 1. Tech 2 will be trying to set it up into a one box, everything you need. Bring it home and do it. And you will be verified on the Zoom with me.
Okay.
So otherwise, no way. We don't have enough room.
Yeah, because I was wondering that I see on this thing right here, you have 70 students. And even if you divide up by 12 or 24, there's no way, even in a week, you could do 70 students.
Right. That's what we have to find a way. Everyone have to be busy. Okay?
Okay, thank you.
Yeah, now you can see very quickly talking about the circuit board here. That's what they're using for the alarm system. You see the display, right?
Yes.
Okay.
Yes.
Now I'll see how they working. Okay, and here you can see just a relay, just like the switch, close and open. And it. This is where they connect you. Just a switch, okay? Where they supposed to connect you.
Is a door or window or something?
Yeah, that connect you wherever you want to connect for your alarm, or the door, the phone, whatever. Okay, so you get 1, 2, 3, 4. Okay, normally try to see what happened. Normally you get a 12 volt here. And everything closed. What happened to that Q1 and Q2?
Is it active?
If you're looking at the circuitry, the way they connect this one, 12 volt here, and that's already closed, everything closed. So what happened to Q1 and Q2?
They
Very close
will
to-
be switching mode, just
They
like a switch.
open. They open.
What opened? Who opened? Which one opened?
When everything is the way it is, R1 and
Q,
R,
the Q1 transistor.
it acts like a voltage divider.
My question is, for this situation, telling me, what happened to Q1 and Q2?
There is no current flowing from the collector to the meter.
So I want the answer for telling me Q1 and Q2.
Q2 is open, Q1 is working.
Okay,
Both will work.
hey,
Both will work.
you can see if they close here, the voltage here will be turned Q1 on, right?
Yes.
Okay. What happened if the Q1 on?
The current go directly to the go to the ground.
That will be telling you the collector here will be connect you.
Ground.
That's right.
Yeah.
Okay. So this look like 0 volt. What happened to Q2?
Not working.
Open,
Open.
right? In this case, Q2 will be open. You see that? The thing is voltage at the base almost 0 volt. Q2 will be open. When they open, that means they cannot connect from the relay to the route, so relay cannot close. They open. So that normally a lamp cannot be on. Okay? And now for example, one of the switches in here will be open. Either one. Right, the first one you connect to the door of your car, or the second one connect into the trunk. Okay? For someone open your door, so that will be open. What happened is that one of the switches open.
Now it's Q2 and you get speaker?
If
The circuit is completed for Q2 and Q1 is off.
exactly. When they open that one, no voltage here. Q1 will be off. Okay? In this case, you get a voltage from 12 volt up to here. Turn on Q2. So that the connect this side of relay to the route will be turned on the speaker. Very simple circuitry for the alarm. Okay, any question on this circuit? I just bring it up to telling you that we very simple application in electronics.
How about a D1 working? We use D1 for what for?
Which one V1?
D1, diode 1.
There is no.
Oh, no, that's inside the relay.
No, inside.
Inside that one.
Hey, Mr. Pham, I got a question. On R1 and R2, and the circuit is set up the way it is exactly right now. Does that R1, R2 section act like a voltage divider? Yes or no?
When you get the voltage here, okay, you
Mhm.
can say you want the voltage at the base. Okay, then you can see that look like the voltage divider. Okay, take that 12 times this one divide total. Okay, yeah. Okay, any more? No?
No, I think your transmission got cut off for a while there, Mr. Pham.
You mean cut off for a while?
For a while there, we couldn't hear you say anything.
Uh-oh. Now you can just hear me?
Yes, yes.
Okay. So basically you're talking about the voltage divider here. Right?
Correct.
Yeah, that's correct. Basically, they just make sure to know you can get a voltage to the base after Q1 to turn it on. And
Okay,
the other
thank
one,
you.
yeah, go ahead.
I was saying thank you, thank you.
Okay, now we go into another one. That will be quiz number 4.
Mr. Pham, I'll have that circuit drawn if you want.
Oh, you want the circuit draw, right?
I just drew that circuit if you want to look at it.
Okay. Quickly.
All right.
That means the switch open.
What was the bottom two resistor values right here?
Let's see, what the value?
100K and
100K and 1 mega ohm. 1 mega ohm.
That's it. That's all that circuit's doing.
Yeah, but you got
Is something wrong?
something's wrong because you got the switches closed and circuit is current is flowing through your coil
What's this?
through the relay.
What's this value right here? What's the value for this resistor?
1.2K, that's correct.
And this one?
1.2K, that's correct.
it might be the inductor. We don't know the value.
That's 1 millihenry. Yeah, either way, it could be one value of 1.
Yeah, your voltage divider on the first transistor on the base is nothing flowing when it's closed. It should be flowing.
Well, if I speed the current up, there it is.
You're missing the 12 volt.
Just moves faster.
How about you open the switch, see what happens?
This is a real troubleshooting.
Yeah. Yeah, when he opened that switch, there was obviously a change.
There
Hey,
was
Lord,
no change. There
open
is
one
no
switch at a
change.
time.
There is no change. The conductor should not be, there should be no current flow through the conductor until those switches are open.
Yeah, there should be nothing on transistor 2 on the base, whereas you do have something going on.
When those switches are closed, current should be flowing to the base of Q1.
Exactly.
And it's not. It's not. It should be going to your voltage divider. It's not going to your voltage divider to establish a voltage at the base of Q1.
What?
And so Q1 is not on.
Okay,
You
now
got Q. So
Go
there's
ahead,
something
Mr.
wrong
Bam.
there.
Go ahead, Mr. Bam.
okay, to just run, I just saw the curve, the current go to the switch.
Yeah, speed it up, you see it. There you go.
That's right.
Yeah,
That is closed.
yeah. Now open it.
Need to open only one. We don't have to open everything.
There
That's
you go.
correct.
Now it's showing correctly.
Yeah.
That's perfect.
Because the first time it only went with the switch closed, it went through Q1. Now with the switch open, it goes through Q2.
Yeah.
That's it. Stop share.
Good
Yeah.
job.
With this software, you guys can design anything you want.
Ready when you are, Mr. Fan.
Okay, so now, here's semi. Okay, so now for this one here, assume the ammeter becomes short to the ground by solder slash or stray wire clipping. What do the meter read when you correct the problem? What do the meter read? If RE will be shorted to round. So now you can tell me what the VBB equal, VE equal, and VC equal. You have to do quickly calculation. In case this one is short to the round. What VBB equal? You know the formula, right? VBB equal 8 volt times 10K divide 10K plus 33K.
I got.
Make sure.
I'm sorry. I got the VBB. It's 1.86 volt.
Okay, you already calculated. I try to say, is it right or wrong? How come they get 0.7 volt?
For a silicon transistor is 0.7. Base to emitter voltage.
You understand it is short to round. That means round right here, right?
Yes.
So from here to the round will be 0.7. You cannot using the formula. You can using the formula to calculate with the RE not shorted. So that's why if you measure VBB, you get 0.7, then RE will be shorted. What VE equal?
Zero.
Zero volts.
Right here, VE here, they shorted to round. They have to be equal to 0. And VC.
Eight volts.
Okay, you say 8 volt. I want to say. How come you say 8 volt?
How we got 49 millivolt?
And they wanted.
How do you get 49?
That's what I say. And they wanted. They don't have to be exactly 49.
What formula you used?
No, no formula.
So if I write 3 millivolts, it's correct?
Yeah, and the millivolt.
Okay. What about 0 then?
If the 0, that means the transistor must be shorted. But the transistor is not on. The thing is you get VBB only 0.7. They can turn the one diode on, right?
Yes.
So that's why anything can be happen, okay? They can turn that diode on. If you get from here to here, is 0.7. So,
Unified school.
so basically, they still get a little current flowing, but they're not working properly. If they open, then you measure right here, you're supposed to get 8 volts. But they're not. Okay, so that is the one they asking for. If it's short, then what happened? And now you have to do a calculation for me. RE not sorted. So one already calculated. 1.8 volt is correct. And VE equal. If you're using the formula, VE equal VBB minus
VB
0.7.
1 point.
Okay, 1.1. And what we see? VC, the formula will be VCC minus
IC times RC.
Right, IC times RC. Okay, I can give it to you that and will be 5.47. Now, we bring it up the problem here, okay? For you, it is in the real work. Your job will be for some wrong with the circuitry here, okay? And when you try to testing, they asking you measure VBB 1.8 volt. You don't have to do any calculation. That's what the test spec, the test procedure, they give it to you. Measure here, you're supposed to get 1.8 volt. And you measure right at the F meter, you're supposed to get 1.6, okay? And you measure at the collector here, you're supposed to get 5.47. That means this one here, they already asking you when you take your measurement. You're not doing any calculation. And also in here, the real thing is they're not asking for measure the current. You cannot measure any current at work. The thing is when you want to measure the current, you have to break the circuit. Okay? And the circuitry, they don't know you can figure or not. But if you break the circuitry, you already damaged the circuit board. So that's why, absolutely, at work, you never measure the current. If they want the current, they will be measure the voltage they divide to the resistor to get the current. Okay? So now, if you measure at this point here, VBB here, okay, do not get 1.8 volt. What do you think any problem? How can we fix the problem? Normally, when you're working, the transistor, it is normally open. They're not short. Okay? And the capacitor, okay, they can be open and also they can be shorted. So now if you want 1.8 volt at the VBB, if you not get that voltage, then what you think wrong? Which one caused the problem?
Bad resistor.
So you understand in the way they calculate, take 8 volt times R2 divided by R1 plus R2. So when you cannot get 1.8, maybe wrong with R1, right? Maybe wrong with R2.
So you're saying the ratio of the resistance?
Probably R2.
Maybe wrong. That means they can be wrong value. They can be open. Okay? That is a priority. The thing is when you want to fix the problem, you measure right here, you get not a 1.8. So don't try to measure anymore here. That's what you have to fix first. So in this case, they can be R1 and they can be R2. And now you can learn a little more. Maybe RE will be shorted. That's why you get 0.7 here. However, most of the resistor is not shorted. They will be open. Okay? So what you need to do? First thing, you can remove the power, disconnect power, and take your meter to take the value of R1. See that? Make sure they will be 33K. And measure the value of R2. Make sure they will be 10K. Okay? And you can check RE, make sure they get a 1K. That's easy to check it. To find out what's wrong. And if you want it, you can check the transistor here. We already telling you how to check it, right? How to check the transistor by the meter. I mean, everything you can check by, remove the power, check in the individual component here. So that will be fix the problem. Okay, after you get this, the voltage is right. And now you measure the VE. You're supposed to get 1.16, but you're not. You can get anything else, but not 1.16. Then how do we do to isolate the problem?
LE damage.
More likely the transistor. Okay? The thing is you get the right voltage at here. Nothing wrong R1, nothing wrong R2. R3, RE, you already check it. Make sure they get a 1K. So mostly the problem is the transistor. Okay? And the last thing when you check in here. Now, if you check in here, you get supposed to be 5.47, but you get 8 volts. Can you tell me what's wrong?
RC is a problem.
Open.
If I say you say a problem, I didn't say anything wrong with RC. If I measure at this point here, I get 8 volts. If RC open, you get nothing.
Yeah.
You cannot
Okay.
get 8.
You get 8 volts there, RC
R1 is
might
open.
be shorted.
If you get 8 volts here,
R1 is open.
RC might be shorted.
huh?
No. I see always short.
What I telling you, resistor considered to be not short, most likely. They can be open.
So the transistor is open.
If they open, then you cannot get 8 volts. Right now, you measure right here, you get 8 volts.
So therefore, there's no current through RC. So
Exactly.
the system.
No current to RC. What can cause the no current to RC?
Hey, Mr. Pham,
Yeah,
you said that RC cannot be shorted.
yeah. Normally, resistor not shorted. They normally open.
Because my reason for thinking that is if it was shorted, you that would give you 8 volts at that point as well.
Yeah, if they shorted. But what I'm saying, normal, they not shorted.
Okay.
Is it because the transistor is off, not working?
Exactly. Transistor not working. So that's why current cannot flow down to the ammeter. They open, that means the current not flowing. IC equals 0. No voltage drop across RC. That's why you get 8 volts. That normally happen.
Well, what about the collector current?
0. The thing is they open, no current flow.
Mr. Pham,
Yeah,
could you tell again how we get the VC by 49 millivolt?
you have to calculate the current IB.
Oh, yeah.
IB, then you can get the IC equal beta IB.
Yeah, I
Then
see.
you can get VCC minus RC times IC. This is a very basically, even you don't have to do your calculation, try to memorize this the formula. It's a basic. When you interview job, they will be asking you. Even they not want you to doing calculation. But they can asking you how can you get VC. VC equal VCC minus ICRC. Okay, and
Yeah, I do.
on this problem. That's what we try to deal with, the real thing happen in the company. Okay, when you're working.
Mr. Pham.
The thing is what I'm saying is you don't have to understand anything. When you're doing the test, they already telling you, I go ahead measure at the base, they want it 1.8. If okay, that means you go to the next one. If it's not, fix your problem. Okay, let's see, next. They say they determine the most probable failure, if any, in the circuit show, based on DMM, read the value, the correct value given in blue. Okay, so basically the circuitry working. VBB will be equal 1.07. VA equal 0.39. VC equal 8.1 volt. That means when you try to test this circuitry, they say, okay, go ahead, measure VBB. They want 1.07. Okay, if it's not, something must be wrong. So now they measure 0.71 volt. That's the first one. What do you think they wrong? I try to give you the answer here.
One, no, R2.
Failure, DMM read 0.7. Peak off, you understand peak off, right? Peak off means properly causing of failure. What the cause given to you did fail. So most of the time, they can say R1 and R2. Okay, more likely. Otherwise, they can be RE. If in case it is shorted, then you get 0.7. We already telling you. Okay. And now, if you measure in here 10 millivolt, okay, when I said you measure here 10 millivolt, what the voltage here at the base? What that voltage? I repeat the question. When you measure at the ammeter, you get 10 millivolt here. What do you think the voltage at the base here?
About
0.7 higher than that.
Now,
See, under 0.7.
Okay.
Now,
Mr. Pham,
now,
one moment. We have a presentation for, look like with Dave and Sandy from the city.
oh, about the
Presentation for the career, for the electronic business owners and from the presentation.
Yeah, just have to remind me. I don't know.
Okay, they're here now. Thank you.
Yeah, okay. I will be stopped there for a while. So let the people from the city want to talk to the guy.
One vote.
Okay, Sandy, you lead.
Awesome, thank you.
Thank
Hi,
you.
everyone.
Hi, Sandy.
I know I stepped into your class briefly about a week ago, and one of the things I shared with you all is as you start seeking career services, my department, myself in particular, I'm here to really assist you in the process. But another thing that I want to do for students, and it's a big focus point for me, is bring industry leaders into the classroom and in front of you to give you just some engagement and learn what's going on, hear from people who may possibly be someone to hire you in the future. It gives you a rare opportunity to really just get to have some open dialogue and hear directly from someone who's working in the industry. So this evening, I do have the pleasure of bringing in Dave Crozier, and he is an electronics professional. He is the president of a company, and I'm going to allow him to speak to you more since he's going to be the subject matter expert in this. But without further ado, I have Dave here for you guys. So I'm going to mute myself. And Dave, hi, welcome.
Welcome.
I think you're muted right now, Dave. You unmute. Almost. Let me see if I can.
Yeah.
Better?
Okay. Yeah, we got it.
Cool. Hi.
Anyway, thank you, Sandy. As Sandy mentioned, my name is Dave Crozier. I'm the president, and my wife and I are the principal owners of a company called Opatech in Carlsbad, California. We manufacture tunable lasers for the medical research industry. So what that means is if you think of a standard laser pointer, you get red or green or one of the standard colors. We can give you every color under the rainbow which
Wow.
means we give you the whole spectrum of color and energy. And that's why they use our lasers. They use them for photoacoustic research. So if you think about an ultrasound machine, if you take away the sound and you use one of our lasers, you would get light. And so photoacoustically, we can give you better results than you can from an ultrasound machine. Actually, you get results that are comparable to an MRI from an ultrasound machine. So we can actually see blood flow while we're doing the testing and things like that. So I had reached out to Sandy, I'm going to say 4 months ago, and we were looking for some electronics technicians to help build our systems. At the time, it didn't work out, but Sandy asked me if I would participate in this and give you an idea of what companies like ours look for. So I'll start out by saying the first thing we look for is we want to know that you're technically competent. And by that, I mean, have you taken the courses? Have you done some of the practical exercises? Have you learned how to do some of the basic things like read a blueprint and solder and things like that? And then beyond that, what we look for, at least in our company, is we look for attitude, in that I want you to fit into our company. We run the company like it's a family. I mean, because we are family. My wife works there. I work there. We know everybody who works with us. And so we look for that attitude and want to know that you're going to fit in, which doesn't mean that you can't push the envelope a little bit. And you should push the envelope. We want you to, to bring ideas and bring some new ideas to the company at the same time. So hopefully that gives you a little bit of a background. I'm happy to answer any questions, or I can't really offer advice, but I'll give you what I can.
Do you have a small piece of gear or anything with you that would indicate what your product looked like?
No, but you can go on our website, which is www.opotek.com. And you'll clearly see it. I'm not very good at Zoom, or I would try and pull it up and share the screen with you. But, quite frankly, I didn't even know how to unmute myself. So,
well, that's part of learning.
Yeah.
Well, Sam will share the screen with you and show you how to unmute, and you can show us how to look at your product.
Well, I've unmuted, so we're good there. But yeah, if you can pull up our website, you can see what we do. We basically take a laser and we run it through some non-standard crystals, and we can rotate it and give you every color you can imagine and every bit of energy. So that's our website right there.
Okay, so everyone can see.
Yeah, we've been in business for 24 years now.
I have a question.
Okay.
I have a question.
Yes.
All right, my name is Lowell Ellis, Dave. Just some general questions. The assemblies that you're putting together are using pick and place?
We are not.
All is hand attached?
All is hand attached.
What's the size of your circuit? What's the size of your circuit
boards?
board?
Are generally we range in size from 3 by 6 to maybe 4 by 8 inches.
Surface mount?
Surface mount.
What's your smallest component size?
Standard resistor.
Are you using microscope sense for attach?
No.
You have some hole through?
We do have some hole through.
All right.
I think we build 50 systems a year, so there's not a lot of circuit board. Most of our assemblies are connecting, our wiring connections, attaching small motors and things like that.
Are you doing any contract work with the General Atomics?
We are not.
All right.
Okay, so
what type of employee are you looking for right now?
We're always looking for electronics people who can step in and help build our systems. Our track record has been that we brought in people at an entry level, and we've developed them up to become laser engineers who do the final assembly and testing on our equipment.
Then you're having the circuit boards designed in-house and then sent out, and then you're receiving your packages?
That's not
Are you-
completely correct. We do some of the soldering ourselves,
Okay.
but we do the design ourselves too. We have an electrical engineer on staff.
When you say lasers, are you growing crystals at all?
No, we don't grow crystals. We buy
All right.
them from China. Yeah. We can't compete. I don't know if you know how to grow crystals, but we can't compete with those large companies that grow crystals.
Yeah, I was just wondering how intricate your service is. That's pretty much what I'm just trying to gather information right now. I know.
Actually, you know, your entire class is welcome to take a field trip up here anytime you want.
Oh, wow. Okay.
We'd be happy to have you, give you a tour, show you what we do, show you how we do it. But you're more than welcome. Just work that out with Sandy, and we'll make it happen.
Sounds good. Thank you very much, dude.
You're welcome.
That would be perfect for me because I live here in San Marcos.
Oh, there you go. So
So I can go take a look at it, and so I
Yeah,
could
absolutely.
provide it the information to the rest of the student.
that would be fine. You're more than welcome.
Okay, sounds great. Thank you, Dave.
Dave, I've got a question. You said you each year you build about 50 units, you said?
Correct. Somewhere between 50. Our best year has been 75 systems.
Okay, so therefore, as a junior tech, you know, that you hire on, what's the duty then?
I'm sorry, what's the what?
What function do they do?
Well, they would come in and begin by learning how we make our assemblies, because we build kits and then we assemble the kits into final assemblies. So you would work in the kit department to start, and then as you handled those duties well, you would move up into taking the final kits and assembling them, and then doing the ultimate testing.
Okay, so I guess there is a lot of component per unit. Time
The
to
average unit has probably, well, the average kit has probably 20 pieces in it. The average final assembly has 4 or 5 kits, so somewhere between 80 and 100 pieces.
Okay.
Without asking you any trade secrets, is this like some type of medical equipment, like in a black box or something like that?
Well, it was probably in a black box for the first 15 years of our existence, but it's not a black box anymore. OPO tunable lasers are standard technology now. Most laser engineers understand them. Excuse me, most medical researchers understand them. It's a way to get a variety of wavelengths out of one laser.
Okay, thank you for the answer.
It's not really a black box anymore.
Okay, thank you.
You're welcome.
But one last question, David Slow again. Since your quantity isn't mass produced, you know, on an annual basis, do you do more subcontract work, or only have your employees come in for a certain time periods when the work is available?
Our employees, we didn't lay anybody off during COVID. We kept all our employees busy the entire time, and we worked standard 40 hours a week. We don't do any contract, temporary basis. It's against the way I believe.
You have an R&D department that puts your whole design through a process, you know, environmental testing?
I'll be rude here, every damn employee we have is in research and development.
Thank you very much.
And one last thing, your equipment is you supply hospitals and clinics and such?
No, we traditionally would supply a university professor who's doing research. So as an example, we sell systems to a Dr. Mayanuta Bell at Johns Hopkins University, and she uses our product. She's attached it to the end of the Da Vinci surgical robot. She has increased brain cancer surgeries at Johns Hopkins University by 50%.
Wow.
And so she's gone and done some research. She's figured out a way to do that. And those are the people we traditionally sell to.
Okay. Thank you.
You're welcome.
I have a quick question.
Yes, ma'am.
For the hiring process, do you guys hire someone with a specific like assemble background, or can be any manufacturing worker that?
Could be any manufacturing work.
All right, thank you.
You're welcome, Viola.
What about the field service rep? Go out and service equipment. Or do you do more in-house?
No, we do send people out. We have 2 people who travel. They don't travel extensively, but they do travel and do installations and repair. But that would be a really senior guy, probably been doing this 5 or 6 years minimum.
You're talking about like an engineer almost there, huh?
Yeah, they're pretty close to being an engineer, but quite frankly, the 2 people we have, neither of them are engineers.
Okay.
They've developed up through our system.
All right, class. Any further question for Dave or Sandy?
Good. Well, we look forward to seeing you. I hope you work it out with Sandy, and you're more than welcome anytime.
Okay, thank you very much, Dave. Thank you, Sandy.
All right,
Thank you, Dave and Sandy.
Yeah, absolutely, guys. Enjoy the
Thank
rest
you.
of the class. Thank you so
Okay.
much, Dave.
Take care.
Bye.
Okay, so we're going back, right?
Yeah, we're back into class.
You ready to pick up where you left off?
Yeah.
Way to go, Wendell.
So to us, what we need, just try to be good first. Okay? That means you know how to do what to do. Then your job will be okay. So now for the circuitry, I repeat it. The value in the blue, that means the value they wanted. Okay? And when they take the measurement here, that means the value happen. And your job will be try to fix it. So the first thing they say, I measure at the VBB here, 0.7 volt, and that is not 1.07. You know what's wrong. Okay? Then normally you can take R1, R2, or also make sure RE. Okay? That is the one causing the problem. And now, when they say you measure,
Huh? Shanti?
they measure at
JB. Yeah, you looking for your mom, huh? I got you.
Yeah, I know.
She's somewhere. She's somewhere. I hear her voice. Sound like she might be in
Put
the
the
bathroom.
micro in.
Mute mics,
Please.
mute all mics, mute all mics.
Thank you, Wendell.
okay, what I'm saying is, when you measure at the S meter, they given you 10 millivolt. So the question is, what was wrong? Okay, so when you measure 10 millivolt here, my question is, what the voltage at the bay here?
Under 0.7.
No.
Oh,
1.
When you measure at the S meter, the voltage here must be correct. If it's not, you have to fix that. So that means the voltage here have to be 1.07 volt.
Mr. Fan, could you repeat it?
What I'm saying here, when you measure at the S meter, then the voltage at the base must be correct.
Yes, but you ask when you're measuring 10 millivolt at the meter, what should, in that case, what is the voltage in the base?
Have to be 1.07. The thing is, if you not get through 1.07 here, you not measure here. You have to fix that first.
is that a reverse bias circuit, Mr. Fan?
What?
Is that a reverse bias transistor?
I don't know. Try now. They say it's wrong right here. But I try to make sure you understand. If when you wrong here, you cannot wrong here. Why? When you measure here, if it's wrong, you must be fix that before you can measure the second one. Cannot be double fault.
We need to check. We need to replace the transistor. I think it's a damage.
Okay. Now let's see what they said. Transistor. That means you get a voltage here, okay, but they will not get the voltage here for 0.39. So what caused the problem will be a transistor.
That's why I asked if that was reverse bias, because the current's going backwards.
Normally you can talking about, I don't care they reverse or forward. I really care telling you something wrong with the transistor. You better change the transistor. And the last one for collector. When you measure the collector, you suppose you get the 1.07 at the VBB already. You already get the 8 meter 0.39. Okay? And now you measure the output VC. Normally, in this case here, like I said, look like the transistor open. Okay? And no current flow through the 8 meter. No voltage drop, so the voltage here and here will be the same. So that's why normally you fix one problem, they can fix that, okay? But it is the way when you try to troubleshooting. First one you measure to get a wrong value, you have to fix that first before you try to go to the next one. The thing is the first one causing the second one to fail. The way for testing, either in digital circuitry or analog circuitry, the same thing. First thing failed, fix that first before try to do anything else.
And what's the third one?
The third one will look like the transistor will be open. Normally, when you want to change it, okay, the way is change the active component. First, what that mean, active component? Active component mean component need the power. Okay, most likely anything wrong will be the transistor. Okay, the resistor will be really hard to fail. Only thing is they put a wrong value on the resistor.
Hey, Mr. Pham, based on the way the circuit boards are made, according to what you've been telling us, so if we're at a company, say for instance, and we had to check the resistors, unlike the current, we could actually shut the power off and check the resistance. Is that correct?
You must. You
Okay,
want to check the transistor, you want to check the resistor, anything, but power must be removed.
Okay.
Okay.
Could we just check the power and the resistance with the the power with the oscilloscope?
In here, nothing to using oscilloscope. The thing is just a DC bias. when you get a signal sideways, then you can use the oscilloscope. On this one here, same thing. VBB is supposed to be 6.56. Okay. At meter, supposed to be 5.9. And the collector supposed to be 5.25. So when you see the DMM measure, you know they wrong at the at meter. So if they wrong at the at meter, telling me which one you think got the problem.
Would this one be RE?
You said wrong with the IE.
RC. Looks like the transistor's open again.
The short one, RC.
Now, you get the voltage at the base 6.56, correct? And they measure the at meter, they get 0 volt. If you at work, then how can you do? Normally on this type of circuitry here, you have to give it to the assembler. You say, I like to replay which one. You have to decide. You want to replay which one?
Transistor.
Transistor, yeah.
Transistor.
That's the correct will be most likely the transistor. I say RE very hard to fail. Normally they can be open, okay? And if they be open to the voltage, they can be anything. However, look like the transistor open here, they're not working. So that's why you measure from here to round, you get 0. So that's why you say, okay, I like to replay the transistor. Now, after they replay the transistor, they give a ball back to you. What can you do?
Isn't that the circuit is wrong?
No. What I'm saying is after you give it the more to assembler to say, go ahead and change the transistor. And after they change the new one, they give a ball back to you. What can you do?
Retest and make sure the numbers are correct.
Exactly. That is the way. You test again and make sure you measure at meter, you get 5.9 volts. That means you get the right thing to do. You get a correct answer. And when you measure the VC, you're supposed to get 7.25. You get 9.
Transistor.
So same thing I already said, right? Transistor can be open. So that's why the voltage drop across RC will be 0. That's why you get 9. That's a very simple circuit. See that? That's a transistor. Now, see this circuit.
Mr. Pham, can you show that last screen real quick?
I cannot change anything. I have to stop. So, okay. Then I try to make it bigger if I can.
No, the last screen you showed where it had the answer. I missed the answer.
Okay.
Well, the thing's being recorded, so you can always go back after class.
Now that transistor. The answer will be transistor. Remove and replace transistor for the lab. Okay, can you see this circuitry here?
Yes.
Okay, that's the only thing we can make. Okay, so you see this one is multiple amplifier. First amplifier go to the second amplifier. Okay, that means you can add in more to increase the gain. Okay, and now at this point here, they're already telling you they get 100 microvolt IMS and 0 volt DC. That's from generator. And on this point here, you get 100 microvolt IMS also including 1.75 volt DC. So you get a 2 voltage here. Okay. And at this point, that point 2, you're supposed to get 6.85 millivolt IMS, and also you can get 5.07. Okay. When they go into the second amplifier here, this point here, you get 6.85 VIMS, and also you get 1.75 volt DC. Okay, and this point here, that point number 4, you get 1.33 volt IMS and 5.07 volt DC. Finally, output here, you get 1.35 volt. So basically, when they want to test this circuitry, you don't have to understand anything. First thing, engineer will be telling you, at that point 1, they want 1.75 volt DC. So you understand that the first one is a CE amplifier. And the second one also CE amplifier. Okay. This capacitor C1 is DC blocking AC coupling. That means only the AC go, not DC. And the second here, C2, what the name? For bypass capacitor. And they asking you, bypass what?
R4.
Bypass R4. That's only telling you for the AC, the signal will current will be go to the capacitor here, not go R4. So that's why bypass. So when you measure at this point, you're supposed to get 0 volt AC. Okay. At the output here, they get 2 voltage, 1 DC, and the 1 will be AC. They will be opposite with the input coming in. 180 degrees out of phase. Okay, and this capacitor, what the name?
That's
DC
coupling.
blocking again? AC coupling, DC blocking?
AC blocking. AC coupling. Why? They don't want any DC from here go to here. Only AC. Okay. The thing in here already you get a 1.75 volt DC. Okay. So that capacitor AC coupling. And will be measure 1.75 volt right here for DC. Okay. And also you get a bypass here. You measure at this at meter, you suppose you get 0. Okay. If it's not 0 AC, something must be wrong with the C4. And the output here also you get 2 voltage, 15.07 volt DC. Another one, 1.30 volt sideways. Okay. And this also DC blocking, AC coupling. That means they allow AC from here go to the output. So basically everything displayed on this schematic, engineer already did it. You only doing a, if you measure the output here, you get 1.35 volt. IMS. That means the circuitry working. Okay. Now,
Quick question, Ms. Brown.
Yes, sir.
And on Q2, the emitter on Q2, you said that's 0, correct?
Q2 at meter.
You said it's 0 volts, right?
0 volt at meter.
Okay, thank you.
That's for AC.
Okay.
Okay, now, like you guys work for me, I build the circuitry here and you follow my instruction to do your job. That means make sure the ball working. The ball working means what? When you apply 100 microvolt at the input here, you're supposed to get 1.35 volt IMS. If you measure right here, you get 1.35. The ball working. Okay? Now, when you measure at the output here, you not get 1.35. You get 0, for example. Something must be wrong. Telling me what you want to do.
What did you say?
When you measure the output here, you're supposed to get 1.35. However, you get nothing. That you know the circuitry not working. Telling me, what can we do?
Is that an AM modulation circuit, Mr. Fan?
What?
Is that an AM modulation circuit?
No, just the multiple state amplifier. Nothing with the AM.
Measure TP4, see if you get the reading there.
That's what I try to teach you guys how to fix the problem. Okay, when you measure in here, you're supposed to get 1.35, but do not. What you need to do is measure at the collector here. Okay, measure here. If you get 1.35, what's the problem?
The capacitor.
C5.
Then now you know capacitor can cause the problem, right?
Right.
It can be open. Okay. However, when you measure at this point, you not get 135 sideways. What you want to do next?
Measure T.
That's 0.3.
T3.
Very good. Go back, measure 10.3. You're supposed to get a sideways. Okay? Two things happen. When you measure, either you get what you want or you not get you want. So the first thing I say, you measure here, you get the sideways you want. Tell me what next.
And your transistors is 40. Request change.
Right. Most likely the Q2, right, can cause a problem. You see that? So when you measure at the 10.3, you're supposed to get your 6.85 millivolt IMF. And now you get exactly that value. Okay? Then you given the board to the assembler. You say, I want to remove, then the new one Q2. Okay? And then after they remove, they replace the new one. You have to test again. That means you have to measure output here to see you get 1.35 volt. If you do, means you fix the board. Okay? Now, when you measure right here, you want 6.85. You not get 6.85. Then you can see, go back here, right? At this point here, that point two. If you get 6.85, telling you something wrong with the C3. Okay? And if you not get 6.85 here, normally you can now recognize going back here. You're supposed to get 100 microvolt. If you do, then Q1. Okay?
You say if you don't?
If you not get here, right? I can see the capacitor C1 here may be open.
It's a process of elimination, right?
Right. That's a process for isolation. More you do, you get along with the way your brain thinking how to isolate the problem. How come when I say the circuitry, your guy measure, I can telling you right away what needs to be done. If you can do it, that's why your job will be more skilled. The thing is sometimes the people know how to do it, that means you can fix it. And the people don't know. Problem is a problem. If you don't know how to fix it, they stay forever. Some people fix for 1 hour. Some people take about a week, still cannot get it done. You see that? Look like you don't know how to do what to do. I've been engineering. I've been working for a long time. That's why technician working with me just for a while, I know for sure. I want to keep him or I want to return him to the test department. Okay?
Question?
Yeah.
If there was an increase in frequency, would there be any change of the voltage or the gain?
No, I don't think so.
If a frequency got higher, wouldn't it fry the transistor?
No, nothing to do with that. However, you have to understand that is the circuit board be built by engineer. Okay, so that means anything you cannot say. They say 100 microvolt, 10 kilohertz, for example. You cannot apply different frequency. You must follow the procedure. Okay.
Well, I'm just assuming.
Yeah,
So,
but that does not happen.
well, at VN, if you put 1K in frequency, you get 1K at V out, correct?
You get a 1K at here, at input here. Output here, you get 1K. Same frequency. Output here, you get 1K. Same frequency. Nothing change the frequency. Still 1 kilohertz.
So the only thing that changes is the amplitude, right?
Right. That amplifier.
Okay.
If one transistor failed, if Q2 failed, if the gate failed and there was an increase in the gain, would there be a change in the frequency? Obviously,
No.
right? No?
No, don't worry about that thing. The thing that cannot happen. I design the circuitry. I telling you apply 1 kilohertz. You cannot change to 10 kilohertz. If you change to 10 kilohertz, the people say you don't know what to do. That's by telling you 1K. How come you can 10K? That means you're asking on the one engineering development. They design, they have to change any frequency to see how the effect at the output here. Okay, and have to select a certain frequency for stable.
Right, exactly. So if you're stable from VN all the way to Q1, and the question is at V out, if we don't have the correct values, and Q2 might be the problem. If Q2 fails, there could be an increase in gain, correct? Or an increase in voltage? What would be the plausible data variables if Q2 fails?
Okay, now if you measure at the TP2, either way you want to troubleshoot it. Two way. One, you going from the output back. Okay, that means you measure output, then you keep going this way. That's the one way. The other way, you're going from an input to the output. Okay? Or, to me, normally I'm doing in the middle. I measure here, if I get the correct,
Nãy
I
mình
go this way.
Đừng chú ý anh sợ nó mở cửa anh té.
Okay? If I'm not get correct, I go backward here.
Smart idea.
That makes a short time to troubleshooting. Measure at the middle here. If it's right, then I go this way. If it's wrong, I go this way.
Mr. Farm.
Yeah.
If we don't have the value of these TB1, TB2, TB3 and something, how we fix the circuit?
If you get the TB which one, TB3 or TB2?
If we don't have the value of the TB1, if we don't have the value given, how we fix it?
Where?
On the value of the TB. How we fix it?
You said we get the not value at TP, right?
Yeah. How we fix?
My question is what TP? You get
Test point.
On the TB. On the TB.
5. When you measure, tell me where.
If they don't given us,
they have to telling you where they measure, what they want. Not you cannot decide that. Like I said, measure TP2. I want 6.85 millivolt. You just follow it and do it. So when you measure, either you get 6.85 or not. That's it.
It really they given the fail ball and they want we fix it. I cannot fix it. I don't have any value.
No, that means when they fail, only thing is normally when you're working in a company, you're working on the circuitry board. Normally you're looking for what they call a TRD, that requirement document. When the engineer design the circuitry, they already put everything in there. That's why you know what voltage from test point 1, what voltage from test point 2. That's only way.
If you didn't know what the voltages were supposed to be, you wouldn't know whether the circuit was broken or not.
If you don't know now, I can tell you one thing, more practical. When you test this circuitry, they fail. And you don't have any information, right? Get the one part, okay? Get the one good one.
The golden, get a golden.
Yeah, get the good one. Take the measure right here, right here, right here, right here, right here on the good one. And now you go into the bad one and looking into each point. If you see the difference, that means some wrong. That is normally happen in a company.
You're saying take a good board and test the good board and bad board against one another and see how they measure at the different test points.
Exactly.
Okay.
That normally happen.
Mr. Pham, I have a question. Like if TP2 was not measuring 6.85 millivolt, what would be the possible problem? Is it the Q1?
Right. That's most likely Q1. However,
thank you.
However, if you check right here, you not get the voltage, you must be checked right here first, right?
Yes.
If you
correct.
get right here, okay, most likely Q1.
Okay.
Hey, Mr. Pham, I have another question.
Yeah.
This is only regarding the sine waves. So at test point 1, test point 2, test point 3, 4, and 5, are the sine waves different sizes at those different test points, or at certain test points, they're one size and then another one, they're another size?
That is only 100 microvolt. That will be bigger. Millivolt.
And that's because this is a we call it a common emitter, right?
Right.
And then you're going to have a certain amount of gain, correct?
Right. So that's why they get 6.85.
Okay, because of the gain.
Right.
Thank you. Thank you.
You take 6.85 divide to 100 micro. Then you know how much they get.
Okay. Thank you.
Okay.
Can I ask a question, Mr. Pham?
What?
Can I ask a question?
Yeah.
So basically, what is the difference between using this kind of circuit in comparison to with a operational amplifier?
They did a common emitter, right?
Yes.
So basically, if you get 100 microvolt here, they amplify, they make it bigger.
Yeah, I understand that. But my question is why this could be better or worse than using an operational amplifier?
Why they get bigger? That's what your question?
My question is why this circuit, or what is the difference between this circuit and using an operational amplifier or instrumentational amplifier to amplify sine wave?
They can be any amplifier.
Okay, thank you.
Okay, this is a transistor amplifier. Next one you can get another one. That's what they call an operation amplifier. Okay.
And Mr. Pham, this is a two-stage amplifier, right? Because this is the Q1, Q2. Both stages are amplifying.
Yeah, they adding more to make it more gain.
And we can make it three-stage or four-stage amplifier by adding transistors.
Doesn't matter.
Okay.
Okay. The thing is, you can see right here you get 100 microvolt, but go to the first one only 6.85. However, going another one, they go up to 1.35.
Yep.
They try to make the signal bigger. That's purpose for any amplifier.
Hey, Mr. Pham, I don't know if I'm answering this right, but I think when the other student was asking the question, why would you use an op amp as opposed to the transistor amplifier? I mean, there must be a difference or reason why you would use one as opposed to the other.
The thing that you understand is this one is using the transistor. However, inside the op amp, they get more transistor. Okay? Inside the op amp, they get more transistor to make the amplifier.
So maybe what you got to do is
This is just giving you the basic amplifier. Inside the operation amplifier, you get more amplifier inside.
Okay.
Okay.
So it's probably better to use a operational amp.
Right.
But maybe it's going to be a little bit expensive in comparison to this, right, Mr. Pham?
Depending on the application, it's hard to say.
Okay, okay.
But if you're looking inside the op amp, you can see too much transistor inside. Okay?
Okay, got it.
When you're looking into digital circuitry, you can see too many digital capacitor transistor inside. Okay? So we'll see you tomorrow.
Thank you, Mr. Pham.
Thank you very much.
Thank you.
No problem. Okay.
Thank you, Sam.